gas and oil are produced together, the gas pressure after separation is often too low to meet the processing requirements of a large plant like this one. Gas pressure also needs to be at levels high enough for proper handling through pipeline sales facilities, gas lift, and injection purposes. So compressors are used to raise the gas pressure and meet these high pressure requirements. This is the first section of a three-section module covering centrifugal compressor principles. In this first section, we'll find out why gas compression is important. We'll also look at the major parts of a typical centrifugal compressor and how it works. Then we'll introduce you to multi-stage and axial compressors. Commonly, you'll find two main types of compressors in use today, the dynamic and positive displacement. Now, the most common positive displacement compressor is a reciprocating compressor, and the most common dynamic compressor is a centrifugal compressor. Every day, someone around us uses some kind of centrifugal compressor right in their own home. This hairdryer, for instance, is a type of centrifugal compressor with a heater. Even this vacuum cleaner is a type of centrifugal compressor. Now, in the oil field, the principle is basically the same, only the hardware is different. Centrifugal compressors we use are usually purchased as a compressor package. That is, they're made up of a compressor and several other components. So let's take a look at a typical compressor package. A compressor package is made up of a compressor, a driver or power source, and often a gearbox. Couplings are used to connect the shafts of these major components. Also, you'll find that most centrifugal compressor packages include a seal oil system and a lube oil system. These can be identified by the maze of smaller piping surrounding the compressor package. Sometimes a gas cooling system is also part of the overall package. Now that you've seen the major components of the compressor package, let's take a closer look at what these components do. The compressor is the largest and most easily identifiable part of the entire package because of its large casing. This is where the internal parts of the compressor are housed, and it's also where the gas is compressed. Inside the casing are two special gas passages that form the stationary part of the compressor. These are the inlet guide and the diffuser, or discharge volute. The rotating part of the compressor is called the rotor assembly. The rotor assembly consists of a shaft and one or more impellers mounted on the shaft. As the rotor assembly rotates, each impeller delivers energy to the gas. The rotor assembly shaft is supported by bearings. The bearings prevent the forward and backward, or axial movement, and the side-to-side, or radial movement of the shaft and impeller. A lube oil system provides the necessary lubrication to the bearings of the compressor. Often the same lube oil system will provide lubrication to the driver, gearbox, and couplings. Seals prevent the compressed gas from leaking out around the shaft. In addition to seals, most compressors have a seal oil system to further limit gas leakage. This seal oil system can either be a separate system or part of the lube oil system. The driver is the part of the compressor package that supplies the power to the compressor. It can be an electric motor, a steam turbine, or a gas turbine. A gearbox is often used between the driver and the compressor. This allows the compressor to run at a different speed than the driver. This gearbox may either be a part of the compressor casing or it might be in its own separate housing. The driver is connected to the compressor or gearbox through either a flexible diaphragm coupling or a gear coupling. The coupling allows for small misalignments between the two rotating shafts. And that's a typical centrifugal compressor. Now let's take a closer look at compressor operation. When gas enters the compressor, several forces are acting on the moving gas. One of these forces is aerodynamic. An aerodynamic force is the same force that causes an airplane wing to lift as it moves through the air. This lifting force helps to move the gas from low pressure at the eye of the impeller to high pressure at the outer edge. Another of these forces is centrifugal force. Centrifugal force is the same outward force children feel when they ride a merry-go-round. As they move away from the center of the ride, the children feel a much higher outward force that can throw them off the ride. Gas enters the compressor through the suction port and is directed to the center of the impeller. As the impeller rotates, the gas rotates with it. This circular motion generates the forces that lift and move the gas away from the center of the impeller, as well as creating a suction at the center of the impeller. Because the outside edge of the impeller travels faster than the center of the impeller, the gas is forced to increase its speed as it moves outward. The two forces, the lifting force and the centrifugal force, increase the motion energy or kinetic energy of the gas. As the gas leaves the outside edge of the impeller, it enters an area of the casing called a diffuser or volute. The diffuser is designed so that the flow area increases as the gas leaves the impeller. This increased area allows the gas to slow down or decrease in velocity. As the gas slows down, the motion energy is converted into increased pressure. Finally, when the gas leaves the compressor, the combination of all these forces, centrifugal force, aerodynamic force, and change in velocity, will have produced a gas discharge pressure that is several times higher than the suction pressure. Well, as you can see, a centrifugal compressor involves several forces that increase the pressure of the gas. But what do you do if the discharge pressure still isn't high enough to meet processing requirements? How do we boost the pressure even higher? Well, typically in the oil field, we use a multi-stage centrifugal compressor. In any typical centrifugal compressor, the force that's created by the impeller depends on three characteristics: impeller rotation speed, impeller diameter, and impeller shape. Because each of these characteristics has practical limitations, there's also a limit on the maximum pressure only one impeller can produce. So generally speaking, the pressure produced by one impeller won't be enough to meet many oil field needs. This is why multi-stage centrifugal compressors are most often used. Multi-stage centrifugal compressors are formed by joining several impellers together, each separated from the others by a diaphragm. Sometimes one impeller and one diaphragm define a stage. In other cases, however, a stage is defined from the beginning of a suction port to the end of a discharge port. In this case, the stage could have more than one impeller in it. In any case, the gas leaving one stage will always be at a lower pressure than when it leaves the next stage. In this way, pressure is increased in each stage until the final pressure is reached. In multi-stage compressors, the gas leaving an impeller of one stage flows through its diffuser and around a diaphragm. It's then directed by the inlet guide into the eye of the next impeller, where once again pressure is increased. By now you should have a fairly good understanding of how centrifugal compressors do their job. But there's another type of compressor I want to briefly cover with you now. It's called the axial compressor. Although the axial compressor is quite a bit different than the centrifugal compressor, it has similar applications, performance characteristics, auxiliary equipment, and even maintenance and operation procedures. In an axial compressor, the gas flow is along the axis of the shaft. Wing-shaped rotor blades attached to the shaft produce aerodynamic forces similar to the jet engine or to an airplane's propeller. As the blades of the compressor rotate, they cause the gas to move in a spiral or helical motion around the shaft. After the spiraling gas moves through one set of rotor blades, it passes through a set of stator blades. Stator blades are stationary and attached to the casing. They act in a similar way as a diffuser, by decreasing the velocity of the spiraling gas and increasing its pressure. In this first section, we've seen how and why gas compression is important. We identified the major components of a typical centrifugal compressor and examined its operation in detail. You also saw how gas flows through multi-stage and axial compressors. Now, in our next section, we'll show you the centrifugal compressor in greater detail. Okay, take some time now to stop the videotape and think about what we've covered so far. Then fill in the blanks and answer the questions in your student manual. I'll see you when you're finished. Now, as you saw in the last section, the centrifugal compressor is made up of several components: the casing, the impeller, guide vanes, the diffuser or volute, diaphragms, bearings, and seals. In addition, most compressors also include a separate lube oil system, seal oil system, and a gas cooling system. In this section, we'll look at each of these in more detail. This is the second section of a three-section module covering centrifugal compressor principles. In this section, we'll examine the parts that make up the centrifugal compressor, and we'll look at its auxiliary systems. In centrifugal compressors, there are two primary casing designs: horizontally split, otherwise known as axial, and vertically split, or sometimes known as radial. This split in the casing provides a means for reaching the internal working components of the compressor for repair or replacement. In addition, the material used to make the casing is determined by factors such as stress, temperature, and corrosion. In the horizontally split casing, the split runs along the center line of the compressor. The main inlet and discharge nozzles, side connections, and other attachments are often built into the lower half of the casing. This allows the upper half of the casing to be removed for ready access to the compressor shaft, impellers, and bearings for internal inspection and maintenance. Horizontally split casings have split diaphragms, which can provide a potential leak path between stages. Also, at higher pressures, horizontally split casings are difficult to seal along the split line, so gaskets are used to seal against leaks. One final note about horizontally split casings. Because there's a possibility they might leak at higher pressures, they're seldom used above 400 psi. Now let's look at the vertically split casing. Vertically split casings are used in most single-stage and higher pressure multi-stage applications. The design of the vertical split reduces the wall thickness needed to confine the high pressure gas, and the smaller seams at the end plate allow for easier sealing. There are several vertically split configurations. One type consists of a cylinder with a removable end plate. When the end plate is removed, the shaft, impellers, and diffusers can slide out much like you'd take the batteries out of a flashlight. These working parts are often called the bundle. The bundle is horizontally split to allow installation or removal of the rotor as a unit. Another type of casing construction uses a vertically split outer casing or barrel and a stacked rotor and inner bundle. This is made up of several donut-shaped parts with vertical joints that form the